the significant part of that lecture, and I think it started to recording. So yeah, so this will be continuation of the liquid propulsion part.
Is my slide visible?
Yeah, we just see outline. I think you need maybe full screen. Just do full screen.
So 1 second. Okay, so now it should be visible.
Now it's good. Yeah.
Okay, I'll just go to the 33rd slide. So, all right. Okay. All right. Hello, everyone. This is Anmol. I am Professor Dr. Kaider's PhD student. I'm going to talk more about chamber cross-section area. So this is the combustion chamber for the rocket, liquid propellant rocket engine. And we would start with a diagram, as you can see in the slide. So AC is basically your chamber area. A star is basically your throat area. And you can see in the diagram, based upon the chamber and the throat area, you will find out the ratio in the next couple of slides. So the below, in the bottom, the relation of stagnation pressures is given, which is a function of your M1 and M2 Mach numbers. So the chamber pressure usually stays constant. We assume it to be constant, but because of the acceleration of the flow and effect, because of the changes in the heat, the pressure falls. But like for our calculations, we assume it to be constant. So the another equation for, and also regarding the pressure, there's another equation for static pressure as it can be observed is 1 plus gamma m1 square divided by 1 plus gamma m2 square. So here, let us assume that the Mach 1, M1 is very, very small, let's say less than 1 Mach number. And if we do that in both the equations, in the stagnation pressure equation, which is this one at the bottom, as well as the static pressure equation, the M1 into gamma term, basically, or in the stagnation pressure, gamma minus 1 divided by 2 into M1 square, this term basically can be neglected. So after neglecting that, we will get the final equations, as you can see, is only a function of Mach, the exit Mach number, or the M2. So using the M2 value, we can also come up with the equation, which is an isotropic equation for nozzle, to calculate the ratio of the combustion chamber area divided by the throttle area. So throat area. So now, why do we need these equations? We need these equations in order to design the combustion chamber of the rocket. So, and the nozzle. So like this equation can be used based upon the Mach number that you desire. You can find out the ratio, or vice versa. You could have decide a ratio, and based on that, you can find out what the Mach number would look like for that kind of system. And you could also do a plot, basically, just to see how it varies with the Mach number. So this graph basically shows you variation of the Mach number M2 with respect to the ratio of your combustion chamber area to the throat area. One thing is quite interesting to see, and this is basically for different types, the 3 different types of combustion chamber designs. As you can see on the top, a longer combustion chamber with a lesser area, and with increment towards the x-axis, you can see a bigger combustion chamber. So one thing you see in this graph is very interesting to see is that if the value of M2, so previously in the last slide, as you saw, that M2, the area ratio is primarily dependent upon M2. It's not dependent upon M1 because we are neglecting that. And so you see at the Mach 1, when M2 is equal to 1, the ratio is also equal to 1. So that's quite interesting to see. And if you substitute that value in the equation itself, so you should get something like that. So now I'm going to talk about some of the propellant feed systems. So we know that a liquid propellant engine requires your liquid propellant as well as the liquid oxidizer, because you don't it's not an air breathing system. You need an oxidizer. If you're going to space, you don't have air over there, so you need an oxidizer. So now the question is, how do you supply that much of fuel and oxidizer in a form of ratio in a combustion chamber? Like a rocket engine is a huge engine, and you need to have like a very powerful system to feed the propellant and the oxidizer to the combustion chamber. So in order to do that, there are different systems. So one of the systems is showed here, which is also known as pressure fed system. This is just to give a small idea, and in detail we will be discussing in the next few slides. So here you can see you have a nitrogen tank on the top, which is very highly pressurized, and then we have a regulator. And what is happening is the nitrogen gas is pushed into the tanks of fuel and oxidizer with a certain pressure. And because of that push, it further pushes the fuel and the oxidizer at a very high flow rate into the combustion chamber. And this kind of a system has a limitation, which primarily is dependent upon the size of the rocket. So if you have a very large rocket and or the weight of the tank, that can be a prohibitive factor for using this kind of a system. Also, you need to design like very high pressure containing very high like great quality of tank, or like a tank which can sustain that high amount of pressure. So some of the propellant feeding systems we will discuss about now. So on the top, you can see these are three liquid propellant engines that have been used in the past. And I'm sure like some of you must be familiar with like the SSME, which is the Space Shuttle Main Engine. Uh, so these are the flow rates. So can you imagine like you need to have flow rates of 250, 468, and 2600 kilograms per second. Like that's like insane amount of flow rates uh, going into the combustion chamber. And how are you able to do that? Like it's a feat of designing design engineering feat of itself. Like it's a great thing that these designers have done. So these so these so in the engines mentioned above, so you see RP basically stands for rocket propellant, and LO is basically your liquid oxygen as an oxidizer, and LH is basically your hydrogen as as a propellant. So as you can see, the delivery pressure for pumping, like this amount of mass flow rate for SSME Space Shuttle Main Engine was around 45 megapascals, which is like extreme amount of pressure. And for hydrogen pump, it was like for the hydrogen engine, it was 55 megapascals, which is somewhere around 6,500 or 8,000 psia. And the main challenge is, how do you design a turbo machinery? How do you design a system which can basically have a less mass, which does not add much mass to your rocket system, and still is able to produce is able to pump that much amount of fuel and oxidizer? That's the main challenge. And as you can see, SSME is a massive engine, and it basically had a world record of basically creating a power density at 100 horsepower per pound, as you will see in the next slide. And discussing about the primary feed system that we discussed in the previous slide, which is pressure fed system, I would again like to go over it, which is basically what you do is you either have a nitrogen or a helium tank, which basically is set up at a very high pressure, I would say like greater than 30 megapascals. And you use a regulator to transfer that liquid nitrogen or the nitrogen or the helium to push into the helium, into the fuel and oxidizer tank, and in order to push them to the combustion into the combustion chamber at a very high flow rate. So this is a simple system as compared to turbo machinery systems, and does not require any turbo machinery or a turbine to or a separate pump, basically to pump in the fuel. One disadvantage is that we need to create like systems with which can withstand like very high pressures, and sometimes the pressures of the nitrogen or helium tank is way more greater than the combustion chamber pressure. So that is one thing that is a disadvantage. So in the table you can see, so if you focus on the SSME engine, you see it can generate 160 kilowatt per kilogram, which is the maximum out of all the listed ones. That's why it's said to hold a world record in order to provide that much amount of power to weight ratios. And here, for different engines, you can see what type of fuel that was required, that was used, and oxidizer that was used. So you can see most of them are requiring liquid oxygen as an oxidizer, and RP, which is rocket propellant one, and hydrogen as the fuel. So these are the main two feed systems. One is your gas pressure feed system, and then is your turbo pump feed system. So we already discussed about the gas pressure or the pressure feed system, wherein just to summarize again is give a quick summary again by saying that we have a high pressure gas which is going to push the fuel and oxidizer into the combustion chamber using the regulators. And now we have a turbo pump feed system. So that's more complex and has also like few more divisions that I will be discussing in the next slides. So this kind of a system, as you can see, we are using a pump and a combination of a pump and turbine, as well as with the gas generator in order to push the fuel and oxidizer. So few people have worked on the possibility of, especially for gas pressure fed systems. So as you can see in the previous slide, they're using regulators. And some people, some scientists have worked on the idea of using and have proposed an idea of using solenoid valves instead of using a regulator. So with the use of solenoid valves, you can basically produce thrust at the chamber pressure in space. So you can use this kind of a system very easily in space. Now the graph that you see here is basically the graph of your orbital transfer velocity, which is delta V required, and like the ratio of your payload to your initial weight. So this kind of a ratio with respect to the orbital velocity, as you can see, the range of using the gas pressure systems and the turbo system. So as if you need like higher delta V, let's say 3 kilometers per second. So for that, like turbo pump systems are more advantageous as compared to the gas pressure fed systems. So these are the three main types of your turbo pump systems, turbo feed pump systems. So the A, B, and C are known as the gas generator, stage combustion, and the expander system. So in the A, so you can see like the pressurized fuel is like basically entering the gas generator, and whatever the product of that pressurized fuel is, it basically drives your turbine, and that is basically sent to the exhaust at the pressure surrounding in the atmosphere, or basically in the space, or basically the ambient pressure. So the example of the engine that is using this kind of system, gas generator system, is basically like F1 or J2 engine, which uses O2 and hydrogen as a oxidizer and the fuel. And the combustion chamber pressure in that case was 5.4 megapascal. Then in the stage combustion system, you see the gas at the exit of the turbine is actually coming from the is actually fed from the combustion chamber, instead of, in this case, in the earlier case it was the gas generator, but here it's the fed basically to the main combustion chamber. And the gas pressure ratio is way more less than it is in the case of A, and the chamber pressure is also higher. As you can see, it's 46 megapascal. And here we have given an example of SSME engine, space shuttle main engine. And then the third one is the expander system. So in this, you can see you don't have any so here what you are doing is you're using all the propellant inside the main combustion chamber. So it's more simple. So you directly use a turbine to pump the fuel and the oxidizer into the system, which is the combustion chamber. And here you have way much lower combustion chamber pressure as compared to it was in the past for situation A and situation B, like for the gas generator and the stage combustion. And also the example that you can use is that is given in this kind of a system is basically your engine RL10, which again uses O2 and H2 engine as an oxidizer in the fuel. So it all depends upon how much thrust you want. So how much, what would be the size of the system, and what would be the chamber pressure. So these are the three main criteria. Like if someone asks you what type of feeding system you want to use, so these are the main three criteria, which is the required thrust, the engine size, and the combustion chamber pressure that you need to basically fly this to operate the system at. So another type of system is your expander cycle system. In this, you can see the fuel is basically used to cool down the nozzle, and the gas which is produced. So it acts like a heat exchanger. The gas which is produced is basically sent to the turbine, and that basically again sends it to the combustion chamber. So it's basically like a closed cycle for this kind of a system. And you can see the control valves are shown here for pumping the fuel as well as the oxidizer to the combustion chamber. So you can see a graph over here, which is kind of similar to the graph I showed in the past, but here it is the burn time versus the thrust. And as you can see, if you want to generate less thrust, so pressure fed kind of a system is more important and useful in like space, wherein you require less thrust as compared to when you are basically lifting off from Earth and you are still in the atmosphere and are about to use a liquid propellant engine. So for higher thrust and higher burn time, you would require something like a turbopump system. And it's a trade-off between like what would be your thrust and the burn time. Like I discussed in the previous slide, is the main, just to summarize again, is that the main reason to use either of those two would be your thrust or the combustion chamber size or the size of this of the rocket or the and the combustion chamber pressure. So these are the main reasons based on which you can decide what kind of a feed system you can use. Then we will talk a little bit about the propellant injectors. So obviously you want to not just pump, but you also want to inject the propellant. So how the design of injectors are. So you can see, you can calculate, it's a function of, it depends upon the Weber number, WE, which is a function of kinetic energy divided by the surface tension. So here in the diagrams, you can see there are three different types of injectors. You have, injectors basically individually giving out the oxidizer and fuel. And then in the second case, they are basically mixing, and that mixture is going in towards the chamber. And then you have a third type of system in which you have an orifice in which the mixing is much more effective, and all of it is basic. All the injectors, their mixing is properly done, and through the orifice, it goes into the combustion chamber. So here you can see a picture of a SLS launch system. So some of the features of this kind of a system is that this is a 300 feet tall system. So it's a huge rocket, like it's a massive rocket, and it's a feat of design engineering itself. And it produces 5.75 million pounds of thrust at liftoff. So the propellant tank is a very important component of rockets, I would say, is because that's actually the one which actually adds the massive amount of the weight to your system, to your liftoff system. So when during the liftoff from the ground, you see like there's a lot of systems attached to the rocket, and the propellant system is the one which consumes, which is actually going to affect your momentum or the inertia so much because it occupies a lot of mass into your system once the propellant is over. And can you imagine like this amount of propellant, like 537,000 gallons of just cold liquid nitrogen, only for 8.5 minutes of burn. So just to escape the Earth's Earth's atmosphere, or like to travel up to some kilometers altitude, you need to use this much amount of fuel. So that's very like a very difficult task. That's why like scientists are, and it also obviously is very expensive. That's why people like Elon Musk or SpaceX companies or different companies are trying to have worked successfully on trying to use reusable rockets so that you could save a lot of cost. And the diameter is also huge, like that's like 27.5 feet for this for 130 feet long length. So regarding propellant tanks, so propellant tanks undergo definitely like two main types of stresses and loads. And I already discussed about like how they do, they are very much affecting your total weight of the system. So they are a very significant part of your total structural like total mass. So the two main types of two main types of loads are your static and dynamic load. So static load is basically dependent upon your fluid in the chamber, the fluid in the tank. So that creates a hydrostatic pressure, and it applies force towards the wall of the tank. So that is your pressure into the area. Then the pressure upon area, and then uh, pressure into area, sorry, not upon area. And the dynamic load is basically dependent upon like when the system is when the rocket is actually flying or like trying to escape the Earth's atmosphere. So you have different types of loads that are applied to the tank, which is aerodynamic load due to the geometry of the vehicle. Aerodynamic load, such as you will have like dynamic pressure, half rho v square, because of your geometry. And then you have the thrust vectoring. So when you are using thrust vectoring, you have loads, like tremendous amount of loads on your tank. And then also because of its inertia. So in order to design like what would be the thickness of the tank, we have a basic equation, which is a function of the radius of the tank and yield stress and the pressure. So based on that, let's assume a design of a three-stage propulsion system. And based on this design, if we calculate what would be the required wall thickness of a titanium wall, so we would just substitute the value from the previous equation, which is the length is around 2 meters, and sorry, the radius is around 2 meters, and the pressure is 100 atmospheric divided by the yield stress. So you get like you need around 1 centimeter thick. So it has to be 1 centimeter thick in order to sustain that much amount of loads. Thank you. If there are any questions, please let me know. So, So if you guys have any questions, you can let me know. I'll be here till everyone exits, and you can feel free to like exit. And whosoever has not submitted the quiz, please do submit it as soon as possible. And please also forward the homework 5. I think I've received most of the homeworks, but if you still have to do it, please do forward it to me as soon as possible.
Thank you.
You're welcome.